I think we can start. We are already about 50 participants here. So once again, good evening or good morning to everyone, and welcome to this new webinar. And today, the presenter will be Professor Fabio Di Trapani, which is associate professor here in Italy at the Politecnico University of Turin. And he will talk about high-fidelity micromodeling with OpenSees and STKO. So frame-infill reinforced concrete frames. And we'll talk about his recent application of OpenSees and STKO in his current works. So please, Fabio, you can start whenever you want.
Can you hear me?
Yes, we can hear you.
Okay. Thank you very much for your presentation and for your invitation to give this webinar. I'm very happy to do this and to share this part of research that we did at Politecnico di Turin, but always supported by the ASDIA software team. And I will leave after my presentation some 10 to 15 minutes for some applicative example by Marilisa Di Benedetto, who is PhD at Politecnico di Turin, supervised by me, that we will show more in detail some specific details in STKO. We will talk about in this webinar about micromodeling, and we will show some application to infill frames. So in general, when we face modeling in engineering, we have to focus the dimension of the problem. So we can go from microscale models to macroscale models and reduced order modeling. Of course, as you can see from the arrow, the complexity and of the solution will increase. The complexity of using this kind of model increases by moving from simplified to microscale model, and also the accuracy. The computational time can be also considered, but by the way, each time the choice depends on the specific application that we are going to face. I want to give some examples. For example, by considering masonry structures, the use of microscale models, I'm taking some very nice pictures from papers from Massimo that everybody, all of us know, based and also on the way of modeling the mortar interface layers by continuum elements, by interfaces. We can give a very nice reproduction of the damage and of the overall and of the local response. To somehow other way of doing this are homogenized masonry. Homogenized masonry is in the middle between a microscale and a macroscale models. It also provides us detailed representation of the damage, and it is good for global and local analysis. Other approaches are, for example, the discrete element model. If we don't want to use FEM, we want to move to DEM. Discrete element modeling can be very useful, especially for describing failure analysis. Other examples, still I'm taking some picture from ASDIA software website. We want to give, for example, a very detailed representation of three-dimensional behavior of concrete and model some very detailed phenomena like cracking and bone slip, or reproducing very specific the effect of reinforcement detailing in the cracking pattern. 3D concrete models or 3D models are necessary to us. These models can be also 2D models, like the one that we will paste in details later, like the one that we have on the right, so modeling infill frame interaction. But in this case, as you can see, we have a high fidelity reproduction of the damage pattern, and we can see again the overall and the local structural response. By reducing the complexity on the model and, for example, going to more practice-oriented solutions, an example for masonry is the equivalent frame model. So equivalent frame models can be, for example, faced by fiber section element or by elastic elements combined with some concentrated plasticity. When we use this kind of approach, we can have a we're not able to again detect the local damage and cracks or something like that, but this is good to get a approximation of the overall response. The same, for example, for reinforced concrete. For example, if we want to consider plastic hinges for flexural response and shear hinges, or fiber section elements and shear hinges, or fiber section elements, shear hinges. And for example, if you want to consider a phenomenological model like the equivalent strut model inside the reinforced frames. All these kind of models are modeled at the macro scale, and we are combining some mechanical models together with some phenomenological assumptions. Okay, this is good to approximate the response, but it is limited to reveal local problems. And finally, we can go to very, very reduced model like the stick models that we are sometimes used for territorial scale vulnerability assessment. We have some examples in the literatures. But if we want to look inside to high fidelity micro.
Patrick.
You can go on. I mute everybody. Muted everybody. Fabio?
See, here, can you hear me?
Yeah, sorry.
Okay,
yes.
Yeah, I'm here. It is possible to, okay, the same here. Okay, so we were saying that the webinar is about high fidelity micromodels. So we will see in this example how we use a high fidelity micromodel for example, they are useful for tracing some physical and mechanical information that we are not able to detect from an experimental test, or that were not detected, for example, if we have a very old experimental test. The other way of using high fidelity micromodels is, for example, the generation of numerical specimen to enrich our experimental data sets. So for example, I have a lot of some experimental tests. They are not enough. I can augment these experimental data sets by adding some very, very high fidelity numerical models. And finally, we can use them for the calibration of simpler mechanical models or analytical models. And our application today is on infilled frames. Going into detail to the infill frames, it's a very well-known problem, but this is still investigated since 1960. Infills, as many of us know, have a key role in the seismic response of RC structures, and they are commonly, in most cases, not included in structural models. So with measuring fields, we have a lot of controversial aspects to consider. We have global interaction effects. Global interaction effects are related to the modification of the overall capacity and all the dynamic response. The resistance will increase by the presence of measuring fields, and the vibration period will reduce. And because of this, the seismic demand will change. Of course, the collapse mechanism cannot be the same, will not be the same of the one that we are expecting for a wireframe. And another important issue that we are facing this webinar, the local interaction effects. Local interaction effects are induced by the contact interfaces that by the shear transfer between the infill and the frame. We have a modification of the internal forces with respect to the one that we are expecting for the bare frames, and an amplification of the shear demand, and potential local shear failure like the one that I'm going to show. As an example, here you can see shear failures at the end of the columns, again at the end of the columns, or also within the joints. This is very common in reinforced concrete frames that are not equipped with seismic response at the end, like the one that are provided by the current, the more recently seismic codes. Okay. For the analysis of infilled frames, we have basically three approaches: the equivalent strat, the multiple strat, and the micro models. So the equivalent strat is one that is the most simple, has a lower degree of complexity and lower computational demand. But because of the concentric disposition of the strat, we are not able to detect local shear effects. So we are not able to estimate the real shear that is occurring at the ends of the columns. Another approach is the multi-strat model. There is a certain complexity in the definition of the contact lengths and on the position of the strats. So this model is very sensitive. And actually, there are some proposals in the literature, but validation has been carried out only at the global level. We have no validation at the local level. And finally, we have the micro models. We have a high degree of complexity, and the computational demand is higher, but we can use them for research purposes, and that is what we will do in this webinar. The analysis of local interaction has been carried out by previous authors. We have some combination of elastic frame with elastic shell elements inside with contact elements, some homogenized masonry approaches that you can see at the bottom, and some, again, attempts to reproduce the distribution of internal force that you can see even with these models is significantly increasing at the ends. Okay. what we want to show in this presentation is what is changing if we are going into detail into the micro modeling of the masonry with respect to this previous modeling. And in the framework that we are proposing, we are first calibrating a certain number of refined model in the way that I'm going to show you. Then we are going to extrapolate the internal forces through the section cut operation that is available on STKO, and revealing the current distribution of the shear and flexural demand on the frame. And finally, finding a way to correct the shear demand that I can expect from a micro model through an empirical relationship. What we are using here is maybe most of you know is the damage TC3D model for the masonry, and the new ISD concrete model that is used for the reinforced concrete. The great advantage here is that we have an automatic regularization of the fracture energy. And what is interesting in this approach is that we are modeling the mortar and the brick as a continuum element. And this is a great advantage because we can either model sliding or mortar joints and also cracks inside the infilled walls. The model consists of frictional interface at the boundary that are deputed to that allow us to model the contact, basically the contact between the infill and the frame. There are basically frictional interfaces, and the model is 2D, but is simple to extend in as a 3D, and we're considering a perfect embedment of rebars inside. The mesh dimension for this problem is very small, but as we will see for the monotonic analysis, by using the OpenSees MP, the analysis will not so slow for this kind of analysis. In fact, based on the size of the problem, this is an example for one of our frames. This is about 20,000 to 28,000 elements. We are using 5 cores, and with parallel computing that is automatic in STKO, we can perform a monotonic analysis in 15 to 20 minutes. By this kind of approach, as you can see, you can reproduce almost with a certain degree of accuracy the experimental damage patterns in terms of sliding of mortar joints, in terms of cracking on the bricks, in terms of shear failures on reinforced concrete. And as you can see, also the overall response is very well reproduced. This is another example with other 2 specimens that we tested in 2014. If you can see maybe we cannot see the video. Okay, I will show you like this. And like this, okay? Okay, going. Okay, so you can see that also here, the damage framework is very well reproduced by this kind of approach. It is very nice to, very well, it is helpful to reveal some extra information that maybe when we did these tests, we were not able to recognize directly from the experimental test. What is interesting to see in the application of, to infilled frames is through the section cut script that is available on OpenSees. In this case, we have discretized the 2D elements into a finite number of section cuts and extracting the internal force section by section by a Python post-processing of the moment and shear, but you can also request the axial force. We can have a real reproduction and a high-fidelity reproduction of the internal force that, as you can see, is quite different with respect to the one we imagine for a simple portal frame subject to a lateral force. And this is very, very interesting to be analyzed because we are interested to check in which cases we are exceeding, for example, the shear capacity, and which are the condition in terms of design and of the infill that induce more or less additional shear demands. These are some examples that we show. We see also during the analysis that the contact length also is varying during the test. You can recognize the contact length from the point where the slope of the shear diagram is changing, okay? Because here we have no contact, this means that we have no load. So since we have contact, we can experience shear. So during the analysis, the contact length of the infield is changing up to higher values. And based on this, we could recognize that based on the mechanical, on the mechanism that is activating during the lateral test, we are having condition in which we have more concentrated shear demand or more spread shear demand, and it is basically changing if the cracking is related more to the sliding or more to the diagonal compression. And if you look at this number is the ratio between the resistance of the brick and the resistance of the mortar. We can see that this number is very important because this is conditioning the failure of the infill in one way or in the other way. For example, if we have weak mortar, you can see this evolution of the shear demand at cracking, at peak, and at the end. Because the sliding will increase during the analysis, you have a modification of the shear demand that is like this. For strong mortars, and that we are going to towards diagonal crushing, for example, you can see that the shear demand is more localized at the end of the column. So this is very interesting to see what happens. It is very interesting to see what happens by changing the ratio between the strength of the units and the strength of the mortars. For example, here we are starting from a case in which we have a sliding of measuring fields, sliding of the infills, and by increasing the strength of the mortar up to 3 times, we can see that we have a change from a sliding mechanism to a diagonal compression mechanism. This is very interesting to see also, even if this is a numerical simulation, this gives the idea on how these parameters are important and can affect the overall response. This is another case in which we are starting from a strong infills in which we have a diagonal compression, and we are reducing the strength of the mortar up to 40%, and you see the change of the mechanism from a diagonal compression one to a sliding mechanism. Another example that you can see is that we did is related to this full-scale frame in which we are reducing the strength of the mortar. And if you compare the first case with the last one, you see how it is changing the crack pattern. So we have diagonal cracks and to somehow some shear damage to the columns in the first case, right? And by reducing the mortar strength, we have the behavior of the field that is much more a sliding behavior, much more closer to the bare frame. It's closer to the bare frame, but if you can see the green line that is basically associated to this last case is still significantly higher with respect to the bare frame. This is the bare frame. So this is just to see how it can be important, the characterization of the materials inside these kind of models. So you can have a reduction of your prediction by 50%. And also, this is something that we have to consider when we are going to design and assess infilled frames. This is one of our main consideration, but this consideration, we could take this consideration thanks to the use of such kind of refined micromodels. These are some examples of how it is changing the local shear demand from considering going to by increasing the strength of the mortar. As you can see, there is a huge increase by moving from the 2.3 to the 0.77 brick to mortar ratio. And on the contrary, here we are reducing the strength of the mortar, and we can reduce the local interaction effect. This is very, again, I want to stress this because it seems from this analysis that the definition of some good design rules for coupling the units of the strength of the units and the strength of the mortar will be desirable, but we have also to consider when we are going to do the assessment. Based on this, we formulated a simplified approach that can be used for doing an approximation of the estimation of the additional shear demand, but using equivalent strat approach. These considerations start from this. So we can consider that the total shear demand is the sum of the drift-related shear, that is basically the one that I can have because of the shear deformation of the frame, and one that is related to this concentration of force that I have here. So basically, the total shear demand that I have at this cross-section of the column is basically the sum of the shear in the frame and the shear in the infill. Unfortunately, with the equivalent strat approach, we are able to estimate only this amount here. So the question here was, can we estimate also some correction for this value and provide some correction for the estimation of the shear demand? So by doing some consideration of the rigid equilibrium of this portion here, we go to a simplified expression that allow us to express the total shear demand as the frame that the shear demand that I can measure on my frame model when I'm using the equivalent strat approach, plus a rate of the axial force, of the current axial force that I'm measuring on equivalent strat, that will be based on some mechanical properties. For sure, it is related to the original horizontal component, but the horizontal component should be subtracted by the frictional forces, and the frictional forces will depend on the contact length. So the major unknown here is the contact length between the infill and the frame. This is very useful application because it allows us to perform some equivalent strat approach, and so taking the advantage of using this simplified approach, but correcting on time, step by step, the shear demand on the frame, so that we will be able to perform this kind of verification with respect to the additional shear demand. And in our test, we can see, I will show the validation in detail, but basically what you can see from the micro model without considering any correction, this is the shear demand on the base column cross section. It is this gray one. The real demand that we obtained from the micro model is this dashed line here, and this is what we get with an approximation of using the macro modeling approach plus the additional shear demand that we are evaluating through this previous relations that I show you. So what we did is basically to create a data set of numerical specimens, or they are not purely numerical. These are numerical specimens reproducing some real experiments that have been validated both with respect to the overall response and on the damage patterns. These are different typologies of measuring fields that include clay masonry, concrete masonry, calcarenite masonry, with hollow bricks, with solid bricks. And by calibrating the contact lengths for all these amount of models, we could establish an empirical relationship for the contact lengths that allow us to give a reliable approximation with that formula that I showed before. So as you can see, in most of the cases, we have a very, very good estimation of the local shear demand that we can extract from the micro model. And these are the final empirical values of the coefficient that we have to apply. This is alpha. The contact length is a product of alpha and n. And these are the experimental numerical diagrams that show us a very, very good correlation between our prediction and the experimental values. Another thing that I want to show you is this final diagram in which we are comparing our approach with the FEMA approach. Basically, the FRIMA approach is much more conservative, and it is overestimating in any case is much more conservative. And the reason why it is much more conservative is because the FRIMA approach is considering only this term here, n times cos theta, is not considering the reduction due to the friction forces. So, of course, we are less conservative, but we are going to more real evaluation. This is the final application that I'm showing you, because people working on measuring fields or in field frames always show results on a single infilled frame. But how this works in a real structure, where the strut and the compressive stress is much more complicated. So, as you can see, we have applied some random section cuts here to check if our model is our predictive model is good enough to estimate the local response. Of course, the solution is not as perfect as the one of the infilled frames, but believe me, this is a very much more complex stress distribution. The stress distribution is much more complex here. But as you can see, the estimation is reasonably acceptable, and again is better than the estimation that you can get by applying the super conservative FIMA model. Again, this is an application to a simplified model, but we have some references, and the references is the shear demand that is extracted by a refined micromodel. That brings me to the conclusion and leaves some time to Marilisa to show some application with this consideration. So basically, the high-fidelity micromodel of infilled frames allow us, but the high-fidelity micromodel in general is quite useful to trace some physical and mechanical information that we are not able to evaluate experimentally, or for example, it is in this case, it is very difficult to evaluate shear demand or flexural demand of an infilled frame during a test. Even if you can do for a new test, but if you have a test from the literature of 30 years ago, for sure this was not evaluated. Then by using a micromodel, you can reveal some information that for sure you are not able to detect from the experiments. In this case, the local shear demand was our goal, and we showed that by performing some parametric study, the local shear demand increases or decreases basically on the unit to mortar resistance ratio, that basically change the collapse mechanism for the field. And finally, we also saw that our micromodeling approach is also useful to find some simplified formulation, to give some reference for simplified formulation for more engineering-oriented models, like the equivalent strut models. And in this case, the combination of the two approaches, the constant comparison of the two approaches, give us very, very interesting results. And of course, this is possible by some extra feature that were recently implemented in STKO, like the section cut. That is very important feature to consider when you have some complicated interaction between structures. And finally, nothing. This was my last comment. I hope you enjoyed the webinar. I would leave some time to Marilisa to explain some details about the models. If you have questions, maybe we can I can answer after the Marilisa presentation. And this is my mail. And thank you very much.
Thank you, Fabio. So now we will leave some room for Marilisa and then for some questions. So in the meantime, if you have questions, you can write it on the chat, and then I'm going to read them for Fabio. Okay, please go on, Marilisa.
Okay. Can you hear me?
They can also open the microphone and also talk, would be nice.
Oh, yes, yeah, sure.
Can you hear me?
Yep, we can hear you.
Okay, thank you. Can you try to share the screen? It is impossible to share my screen.
We see your screen, Marilisa.
It's not my screen.
Oh. Try again to share it.
Okay.
Okay.
Perfect. Okay.
Yes,
we see it.
Perfect. Okay. So now I want to talk about the modeling issues of micromodel in STKO. So just briefly, I want to discuss about geometry definition, physical properties, definition, element, load and constraint conditions, how to make this local interaction between masonry fill and concrete frame, and also some things about analysis setting and post-processing, especially on the extrapolation of the internal forces at the section cut, at specific section cuts. So I want to show you in STKO. So as you can see in the model, the geometry is easily reproduced on the CAD environment of STKO. But of course, if you work better in AutoCAD, you can do it in AutoCAD, and then you can import the geometry with the tool. So I use this type of subdivision of element. So I model the geometry at the level of the masonry unit and also at the mortar joint. I subdivided the masonry unit since I want to do a structured mesh, so we need to have consistency between the subdivision of the elements. So this is the geometry about masonry, but also about the Infilled. We divided the masonry, but also about the RC frame. We divided also the RC frame in this way in order to assign different physical properties. For example, we assign to this line the physical property for concrete cover, and at this part inside the stirrups we assign the physical property of concrete core. So what about physical properties? We define, as Professor Fabio Di Trapani said before, a damage TC material for brick and also for mortar. As we can see in the brick constitutive model, we define the elastic modulus, the tensile strength, and the compressive peak. Then we need to define also the initial elastic compressive state, and then the residual strength. And we set it at 50% of the compressive peak strength, and the residual one is set about the 10% of the compressive peak strength. We define also the fracture energy in tension and compression. We started from the formulation of the model code, where I don't know if I can note something, maybe yes. As you know, the fracture energy in tension is equal to 0.073 FCP in megapascal at 0.18, and then GC is equal to 250 the GT. Okay, but these are starting values, and then we define the calibrated ones. So these values that you are seeing here are the calibrated values for the fracture energy in tension and compression. So if we can evaluate also the constitutive model in compression and in tension, we can use the test, as you know. So we test the compressive state of stress. We need to define the characteristic length. So if we want to visualize the constitutive model in compression of about a specimen of 300 millimeters, we need to set the characteristic length at 300 millimeters. So in this way, this value, the compressive fracture energy of 8 is regularized by this type of characteristic length. So we can test with a monotonic test. How do you know? I can test. Okay. I don't know why the tester doesn't go. 300 is okay. Let's try to increase. Now, I don't know. Maybe there's something. Maybe I can show you for the mortar. Okay, I can show you for mortar. For the monotonic test in compressive states, in compression, we can notice that we have a regularization about the fracture energy in compression, but we can also test the tension in tension. So if we want to visualize, okay, we have also the regularization in tension for this fracture energy, that is the calibrated one. So this is for masonry. The same approach we did also for concrete, but for concrete we want to use the new material implemented in STKO, that is as the concrete 3D. So we use two different types of constitutive model for concrete, the one of implemented for core, and another one that is implemented for the cover. So this is the cover one, the one implemented for the cover, where we have the peak compressive strength related to the experimental tests of the infilled frame. We also calibrate the fracture energy in tension and compression. In this case, the formula given by model code are pretty good, so they are okay for concrete. For confined, we use an increased value of the compressive peak strength, but also an increased value of the fracture energy in compression, since we have also a more ductile behavior than the concrete used for the cover material. For steel, we use hysteretic material, so we define the first the yielding point, then we define also the ultimate resistance, and we drop the curve with a decreasing of resistance. So the test is intention is like this. If you want, you can also reproduce the collapse, not the collapse, sorry, but the ultimate. You can. I can't find the word. You can use min-max to drop this resistance to 0. So if you want to decrease to 0 this resistance, or anyway, you can use this type of constitutive model. Then we use the elastic foundation, since we do not expect any sort of damage in foundation, so we can use elastic foundation with an ND elastic isotropic, just defining the elastic modulus and the Poisson ratio. And finally, we define the section of rebars. So we use section fibers. As you know, you can draw the section fiber here, but the choice is that I want to show is that we want to define the rebars in the depth of the frame. So we define the real diameter of the steel rebars, and this is the layout in the depth of the frame. So if I show you in 3D, maybe we can see better. Okay. Okay, you can see that we have the first layer of rebars, the second layer, and the third layer of rebars. Also for columns, but also for the beam. Okay. And then we give the section properties, the special purpose to combine the section with the integration type. So that's it for physical properties. About the element properties, maybe I can remove these. Okay. Okay. So,
con el diseño que le gusta de la pertenencia, o sea, porque está, digamos, le dicen que la parte de arriba de la viga tiene que usar.
Okay. About the element properties, we use quadrilateral elements since we are doing a 2D model, so we don't need to use complicated elements. We use quadrilateral elements that is compatible with the mesh that we are using. So we are using structured mesh that wants to have 4 nodes definition of the element. This is the element used for infill, for columns, and also for beam and foundation. For rebars, we use force beam element, but it is quite good also use the displacement beam element. Of course, if you use displacement beam element, you know that you need to have a refined mesh, so the response is quite affected by the mesh size. And then the important thing that I want to discuss is the contact elements. We have a contact element that is defined by zero-length contact as implex, where we want to define 2 penalty that is in normal direction and in tangential direction. So since they are penalty values, we need to have high value of penalty, but not high enough value. So we need to put these values in order to have a good convergence. So we don't need to have a bigger value in order to not have a convergence problem. About friction coefficient, we need to set about 0.6, 0.5. It depends on the experimental test. In this case, for this experimental test, we set the friction coefficient of 0.6. About the conditions, we fixed the base of the experimental test. We use load force edge for implement a load at the column level, so at the end of the column, at the top of the column, and then we push with a unit load. Yes, with a unit load. And then we constrain the rebars with an embedding condition. So the rebars are perfectly embedding at the concrete in the concrete matrix. And also in this case, we need to define a penalty value that is quite good to use a penalty value that is 3 or 4 orders higher than the order of the elastic modulus of the concrete. Then we need to define analysis step, recorder. We need to add constraint, add conditions about constraints and SP constraint and MP constraint. We need to add load, and we implement two types of analysis, the vertical one and then the horizontal one. The vertical one can evaluate also the effect about the gravity load, and then the horizontal analysis can compute the effect of the pushover analysis. About the horizontal analysis, I want to show you that we are doing a displacement control. So we need to have a selection set at the top displacement, at the top node for checking the displacement. Of course, we need to set the target displacement, that is the ultimate displacement of the experimental test. And then we do the analysis as we usually do in STKO. So this is for the pre-processing. For post-processing, I want to show you just a curve. We get this type of curve for the micromodeling response. So this is the pushover analysis. And then this is the damage pattern for this type of specimen. But the thing that I want to show you is how to use the section cuts. So if we turn a displacement, okay, in this way I can see. Okay. Maybe mesh size is quite good to see. Okay, I can remove the quad infill and the contact beams and contact columns since I don't want to select any points. And we can extrapolate the internal forces at specific section cuts. So, for example, I have these section cuts. Okay, we need to define just 2 points. So, in order to define the plane where we are integrating the internal forces, so we need to open the script. This is a Python script, and you need to add the script in the folder that you give in the script explorer. Then we can run the script, and then the script asks you to define the local axis for this section cut in order to give to the script the exact plane that in which the Python script are doing the integration. So we need to have a right orientation of the local axis. Sorry. For 2D elements, we need to have z-axis in the horizontal direction and z-axis, sorry, in the horizontal direction, and the x-axis in the vertical direction. So, okay, sorry. We can do it again. Okay, we need to rotate. Okay. And so when we have this orientation of the local axis, we can select the results that we want to have. In this case, we want to select the results for the 2D frame, but also the results on the reverse. So we select force 2 components and force 3 components, and then the script sum force 2 components with the force of the reverse. So we press OK. And we can say that if we want to have the results at the last stage of the analysis, at the end of each stage, or at all steps. For doing what Professor Fabio Di Trapani show you, we need to define the internal forces at each step. So we press OK, and then the script run. Okay, maybe with the connection is a bit low.
By the way, now we can send you a new script. We develop a new script which is much faster.
Yeah, it is a bit low, so sorry. I want to show you the result, but in the terminal you can find all the results, and then you can copy paste to use these and implement whatever you want. So in my case, I want to record just the shear at specific section cuts. So this is what I want to show you this day. So hope you find it helpful, and that's it. So thank you for the attention.
Thank you, Marilisa. So now we have some time for questions. I already can see some question here in the chat. So Fabio, if you want to, I can read it to you and then you can answer. So going from the first question by...
Can you hear me?
Yeah, we can hear you. So
Okay.
The first question is from Camilo Rodriguez. So thank you for the presentation. Could we use this approach to model not only infilled frames, but also unreinforced masonry frames, taking into account out-of-plane effects? Well, in this case, I can also answer by myself. Yeah, you can do it. And we gave a webinar specific on this one. So how to do the same micromodel did by Professor Di Trapani, but with shell elements and loaded in the out-of-plane direction with the same material. And in that case, it was just unreinforced masonry. So you can go on our webinar page and you can see the webinar about out-of-plane micromodeling of masonry, which answer exactly your question. Okay. Then we have another question by, yes, it's exactly this one that Fabio is showing now. Okay. There is a dedicated webinar on this, so you can go and check it. Now we have another question by Kamal Ahmed. So once again, Fabio, thank you for the presentation. So you mentioned that the computational demand is high. Could you give us an estimate of how long it will take to run the model, for example, for a single bay, single story frame? Fabio, I think you already gave
Yes.
estimation time it took in your case, but it really depends on the machine you have. But
yes, this depends on for sure. This depends on the machine you have, but on this kind of pushover analysis for a single story, single bay, it's basically from 15 to 20 minutes to get the results by using OpenSees and and partitioning the model in submodels. This is quite effective if you have more core to use. And it is generally the combination of these OpenSees and that is built in STKO, and the integration method, the implex integration method, will give you a very, very fast analysis time for this kind of model, if compared to other programs, for example. That's why that is my experience. But also, if you go to a bigger model, and if you have a available core, let's say that you have a 24 core, not too much, you can still increase the number of cores and get the result in the same time, even if a bigger model. For this model, we are using only 5 processors. That is the optimal compromise that was in that time, was the optimal compromise between the number of elements, of finite elements, and the number of course, you have to get you have to consider 5,000 to 7,000 elements for core. Okay, so you can maintain more or less the same analysis time by increasing the number of cores, even for the bigger structure that I show you, the 4-story 2-bay ones. So yes, this is something really effective, and allows you to also test the model many times, unless waiting for hours or days.
Yeah, sure. Okay, then next question by Bibar Khan. So you showed an XFEM model in your initial slides. So I have a question about XFEM. So during my research on reinforced masonry structure, I encountered an issue with the XFEM model, specifically when modeling crack propagation. The presence of a single element with a crack followed by additional cracks led to convergence problems and ultimately caused the job to be aborted. So what is the issue? If the issue is relating to the XFEM, well, first of all, probably Fabio, I don't know if you showed some images.
No, I don't remember. But
yeah.
By the way,
Anyway,
Massimo, you can answer better than me.
I mean, XFEM is not in OpenSees, so probably you are referring to Abacus from what I can see from your questions. XFEM is a different way for modeling the crack propagation, and it really depends on the implementation, because it's very difficult to implement. Now, I don't know the implementation details in Abacus. For sure, it takes time, or it's very difficult for the XFEM to achieve convergence, and probably in your case, it seems that it doesn't handle very well crack branching. But I'm just guessing, so I don't know how it has been implemented in Abacus. Okay, so I cannot give you any information about this. I know that XFEM can model crack propagation, multiple cracks crossing at the same point, but it really depends on how it has been implemented and if it has been implemented. Okay, so you have to check with your software documentation for this. And then we have another question by Albert. Oh no, we have a previous question, sorry, by Juan Pantoja. How can I access this STKO GUI for OpenSees? Well, you can go on our website, which is asdiasoft.net, and there you can follow the links for STKO. Okay, you can download the trial version, do your own evaluation, look at the webinars, the user forum. Okay, so just go on the website and follow the directions there. We have another question by Albert. Hi, Dr. Di Trapani. In our place, we usually provide horizontal bar every 3 layers and every 600 millimeters vertical rebars. How these bars affect the model and resisting strong shear force? Does bars help?
Okay, this is maybe typical on non-European countries, but I saw many times in papers the insertion of some horizontal rods in field frames. I think this is helpful, and this will give some more ductility and limit also the potential cracking failure mechanism. For sure, it is something that you have to consider in the model, because the bar will interact significantly. You will have some tensile strength in the part that where there is the separation. So I expect that the model is will experience more resistance, more peak resistance for sure. I'm not sure if this will give some additional ductility. Maybe yes. What could be interesting is looking if these bars can have some sliding after certain cycles in the some sliding and lose their effectiveness during the cyclic analysis or dynamic analysis. But by the way, for sure, they are a good way of building measuring fields. I can also expect to somehow some reduction of the local shear force, because there is some tension force that is balancing, and it is a good topic to be investigated. We have some experimental tests in the literature.
Okay. Thank you, Fabio. We have a few other questions. One from JS Nai, I hope I pronounce it well. So for commercial uses, what kind of license for OpenSees? Does that come with STKO? No. First of all, STKO and OpenSees are two distinct softwares. So STKO is a pre and post processor, OpenSees is the solver, and OpenSees is not distributed with STKO. Okay, so you have to download STKO and you have to download OpenSees. And for OpenSees, you have to look at their licensing. Okay, now just to give you an idea, but this is not very precise as a question. If for commercial use you mean that you want to use OpenSees to do your engineering jobs, in this case you can do it, but you cannot distribute OpenSees. So in any case, if you want a more detailed answer, you have to see the OpenSees legal notice, so the OpenSees license, and you should contact the University of Berkeley. Okay. Then another question by Camilo Rodriguez. Can we use these elements in the academic versions of STKO? Of course you can. There is not a limitation on the kind of elements that you want to use. So sure. And then we have a last question by Shima. Thank you for the presentation. Okay, will the STKO team have a webinar on soil modeling, especially on dynamic analysis and set response analysis? We already gave some webinars about soil modeling and soil structure interaction. I don't know if you had the time to look at them, but yes, we already gave some of those presentations.
We probably will give another with Jose, like on our website when the new materials are going to be out. Exactly,
because recently we gave a webinar with the help of Professor Jose Abel that was hosted on DesignSafe about the use of the DRM, domain reduction method. And with Professor Abel, we are also implementing new material models. So probably we are going to do a new webinar soon. Okay. Okay, I think. So is there any webinar on continuous microscopic modeling in STKO? Yes, we give many webinars on continuous microscopic modeling, microscale modeling, like the one given by Professor Di Trapani. So you can go on our website, you can go on webinars, on advanced webinars, and you can find many of them, okay, both regarding reinforced concrete and masonry. Okay, so thank you everyone for your question. I don't know if there is some other question. Otherwise, thank you everyone. Thank you, Fabio.
Thank you.
Elisa. And thanks to all the participants, and see you again in our next webinar.
That is.
It's going to be next month. The next webinar is going to be next month, and we're going to have Professor Derisi from the University of Bristol as a presenter. Okay, but you will receive all the information in time. Okay, so once again, thank you everyone, and thank you, Fabio.
Oh,
Bye.
the topic. Can you mention the
Bye.
topic? Do you remember?
No, I don't remember. Sorry.
They are asking for the topic of Raffaella, maybe.
Yes. I
Maybe
think it's about wind modeling with like turbine steam
wind
turbine.
turbines, modeling of wind turbines.
Exactly. Correct.
Sure.
Bye.
Okay, thank you everyone.
Bye everybody. Thank you.
Bye bye.
Thank you. Bye.